Hi, I'm Paul. We're doing Leetcode must-know interview questions, and today's challenge is minimum path sum. Given an m by n grid filled with non-negative numbers, find a path from top left to bottom right, which minimizes the sum of all numbers along its path. You can only move down or right at any point in time. And there's an example here. The minimum cost path for this would be if you went 1, 3, 1, 1, 1. What is that? 1, 2, 3, 6, 7. Okay. A couple of ways of solving this. It's a dynamic programming problem. Well, there's more than a couple ways of solving it, but first of all, if you wanted to do it top down, to me, it's more intuitive to do it bottom up, but let's talk about doing it top down. So you do it top down. First of all, think about doing it recursively. Okay, so let's say, where's my cursor? Okay, this down here, the bottom right corner is where you would accumulate the minimum sum path. All right, so you can do it recursively by saying, well, the minimum sum path to get to this bottom right corner would be the contents of the cell, which is 1, plus the minimum of, and let's see, we can go left or down, plus the minimum of the minimum sum path to get to this bottom center cell with the 2, or this cell here, the middle cell in the right column. All right, then how do we figure those out? Well, again, recursively. The cell with the 2, what is the minimum sum path to get there? Well, it would be 2 plus the minimum of the minimum sum path to get to the 4, or the 5. The minimum sum path to the 1 would be 1 plus the minimum sum path to get to either the 5 or this 1 in the top right corner. Okay, so we already have an overlapping subproblem. We have to compute the minimum sum path to the 5 to get the minimum sum path for the 2 or for this 1 in the center of the right column. So we're recomputing the same we're doing the same computations over and over, and this is just a 3x3 grid. How big can the grid be? It can be up to 200 by 200. All right, so the possibility of recomputations there is quite high. If you do this as a recursive solution, your solution is going to be 3 to the power, it's O of 3 to the power of m plus n. That's terrible. So, okay. So then the next step is you convert that to a top-down dynamic programming solution. And you create a dynamic programming matrix of the size of your original matrix, and every time you compute the minimum sum path to a cell, you memoize it, meaning you put that solution into the dynamic programming array. So then as you're going through and you want to get the minimum sum path to some cell, you first check the dynamic programming matrix and see if the solution is in there. If it is in there, you just look it up. If it's not in there, you compute it one time and then you put it in the dynamic programming matrix. So you only have to do it one time. Now that is going to be an O of M times N solution. Okay, that's a lot better. Let's think about a bottom-up solution for this. I'm going to pause this while I draw the matrix. All right, so there is our dynamic programming matrix. Let's do bottom-up minimum sum paths. Well, the minimum sum path to this square cell, based on the matrix that we're looking at, is 1. And it's easy to do the first row if we just go straight across 1, and then this cell in the center is 3, so the minimum sum path would be 4, and then we add one more to get here, and the minimum sum path is 5. It's also very easy to do the first column. So we just go down, we say 1, add the next one, the minimum sum path to here is 2, the minimum sum path to here is 6. All right. So let's keep going. Minimum sum path to this center square is 5 plus the minimum of the square on the left and the square above. So that would be a 7. Over here, the minimum sum path is 1 plus either 7 or 5. It's going to be 5. So we'll go to 6. The minimum sum path to get to the bottom center square would be 2 plus the minimum of 6 or 7. So that would be 8. And for this one here, bottom left, it would be 1 plus the minimum of 6 or 8, which is 7. And 7 is the answer that we want. So that's the bottom-up method. To me, it's a little bit more intuitive, so that's the one that we're going to try to implement. All right, so for convenience here, let's do int m equals grid dot length, and int n equals grid 0 dot length. Okay. And you know, we can put it up here, and we need the DP array. So int DP. Let's do it this way. Int DP equals new int m n. All right, we can initialize the top left. We can initialize the top left. Is that right? Yeah, top left dp00 equals grid 0 0. All right, and then fill in the rest of the first row for int I. Well, actually for rows, let's use j. For int j equals 1, j is less than n, j plus plus. dp 0 j equals dp 0 j minus 1 plus grid 0 j. All right, that is the first row. Now let's do the first column. It's pretty similar. Let's say for int I equals 1, I is less than m, I plus plus, dp, dp I0 equals dp I minus 1, 0 plus grid I 0. All right. Now filling in the rest of the table, we need a nested loop for this. So let's do for int I equals 1. I is less than m. I could have copied this. I is less than m. I plus plus. I guess I could copy this. Oh, you know what though? Really, let's just copy this. For int j equals 1, j less than n, j plus plus. All right. dp I j equals grid I j. It's going to be too long. Plus math dot min of dp I minus 1 j and oh, you know what? I don't have to do it like that. Math min dp I j minus 1. Oh, it didn't fit. I'm going to scoot it over a little bit. Okay. I need one more parentheses here, right? What does that match with? Oh, wait. Okay, hold on. All right. What does that match with? What does that match with? All right. That has got to go. All right, now where are we? Math min dp I minus 1j and dp I j minus 1. Yes, whichever one of those is less, we're going to add it. All right, close the for loop, and we are going to, let's see, we are going to return the bottom right corner, which would be dp at m minus 1 and n minus 1. I have too many brackets here. if we get rid of that one. Okay, that looks right. All right, so we've got M and N. We construct a DP array. We initialize the DP array. We fill in the first row. We fill in the first column. We iterate through and get minimum sum pass to the rest of the squares. Once we filled the dynamic programming array, we can return the bottom right corner. Let's try it. Compile error, int, oh, too many parentheses, I'm sorry, brackets in there. I don't think this one is really an error. It's just a carryover from the first error. Let's try it again. Oh, it is still an error. Okay, 15. What's up on 15? EP, oh, I see. Typos. All right. Let's try it again. Accepted. Good. Let's scoot this over, submit. All right. 4 milliseconds. I'm trying to think. How can we do this in... Oh, yeah, I suppose. No, but that wouldn't be faster, I don't think. I mean, so top down or bottom up is O times M of N. Let me think about this a little bit. I guess maybe that would improve it by a constant factor, I guess. We don't need to store the whole DP table. The current state, to get the current state, we really only need the values from the previous row. So we don't have to store the whole thing. So we could space optimize it a little bit, but that shouldn't affect the runtime. Anyway, this is the most common runtime. So I'm not going to worry about it that much. Let's do complexity here. M times N. All right. And that's it. Please feel free to like, subscribe, comment, and see you next time.